So, hey everyone. I hope the homework went okay. This was sort of the most theoretical a homework really is going to get in this class. We're going to start moving more towards the applied stuff now. One thing I wanted to remind us that our midterm is this coming Monday, and the midterm does cover everything up through this Friday. I know that's it's kind of nasty, but it is sort of a consequence of doing a whole semester class, squeezing it in 4.5 weeks. So definitely start reviewing the material that we've gone over since the last midterm, and really try to stay on top of the homework up through this Friday so that you're ready for the new material we're doing through the end of this week. And practice problems are posted. I think I'm going to plan, I think my Thursday night is dedicated to starting to building those solutions up. So hopefully we will be well prepared for Monday. So I wanted to start today with a recap of the Central Limit Theorem. And what I mean by that is I hope we have at least a general, if not nuanced, understanding of this pretty interesting theory in statistics. But I've gone over a lot of different ideas, and I've boiled everything down to right here, what you need to know for a test kind of situation. So I'm gonna do a recap, and I'm gonna lay out the important points. So the Central Limit Theorem recap. And if I were a cooler professor, I would have made it into a rap, but I'm not. So the sample mean. The first big idea is that the sample mean, x bar, is itself a random variable. And like all random variables, we can calculate an expected value invariance. And I actually gave you the formulas for these. So this was expectation of x bar turned out to just be the expectation of the data from which we made x bar, which is mu. And let's make this very clear. This is the average of the population from which we sampled to make x bar. Okay, so that's what that number is. And x bar is a random variable. It has this expectation, and we can also calculate its variance. In this one, I gave you that it's equal to the variance of the whole data divided by n, which is sigma squared over n. Whereas this is the variance of the population. So the population from which we sampled to make x bar. And this is the sample size. The size of that sample. So the next big idea was what I called the central limit theorem. And that was, under certain conditions, x bar's probability distribution which is, just as a reminder, probability distribution talks about what values it can take And with what probability it will take them. So X bar's probability distribution under certain conditions is approximately a normal distribution. And that was the thing that we called the central limit theorem. So a normal distribution, and we already calculated this, but I'll also put it down, with mean mu, which is the population standard, the population average, and standard deviation, sigma over root n. Okay? So these were the two main ideas. One is that X bar is a random variable with this mean and this expected value and this variance, and that further X bar has a distribution, and under certain conditions, it's normal. So these are the two big ideas to remember from these last few lectures. And the other things to remember are the conditions that we need, that I refer to right here, to use the central limit theorem. One, your original data values that you got in your sample, the data values you use to calculate your sample mean, they must be independent. And we got this. So previously in this class, we achieved this by taking a simple random sample of less than or equal to 10% of the total population. Okay, so the first condition, you need independence. And the way that we have done that in the past is just saying, my sample, it accounts for less than or equal to 10% of the whole. Therefore, I can get, it's approximately independent. This condition is therefore satisfied in that case. Second thing is your sample size, n, must be large. Typically, we look for sample size greater than or equal to 30. So something actually that my last section brought up is that these two conditions may seem like they kind of contradict one another, right? Number one, I'm talking about take a sample that is small enough so it's not bigger than 10% of the total. And then number two, I'm saying take a really big sample, right? These seem to sort of like not work together, but they need not be disjoint. They certainly can both happen simultaneously. And the point I want to make is the population is usually huge, right? So if I were to have, I think I used octopus tentacles, right? If I were to look at the whole population of octopus tentacles, maybe this is 1.5 million, right? So many octopus tentacles. And in this case, what? 10% of 1.5 million is, oh goodness, I should really know this. It's 150,000, right? So I could take a sample size that is greater than 30 people, but still less than 10% of my whole population very easily. And in fact, a lot of samples usually fall into that category. For reference in problems, this first condition, I cannot think of a problem I've ever written where this condition is not met. As long as you have reason to believe that your population is really, really big, you're probably good. If you're dealing with a population that's relatively small, then one, why are you using the central limit theorem? Just take a sample that is your entire population and then you would know everything, right? And two, in that case, yeah, you should probably think about condition one. So I just wanted to make that point because this confused a few people. I have these two conditions that seem like they contradict each other, but they don't. Okay? We feel good okay about this? Yeah? All right. Our third condition is that the distribution of our sample is not strongly skewed. And this, if you have a distribution that is very, very skewed, it can mess with the central limit theorem. Like technically the central limit theorem will still work, but it becomes much less accurate. So what I want to say is you should check your data to see if it's strongly skewed. If it isn't, great, keep moving forward. If it is, I want to make a note that if this does happen, we can still proceed given our sample is much larger. So if this does happen, it doesn't necessarily mean that central limit theorem is off the table. You just need a much bigger sample for it to work. That's kind of the solution to this skewness problem. So I mentioned this because a lot of times when we have people do problems, you're dealing with sample sizes like 100 or like 60 or maybe even like a weird small one at 35. I will mention though that in today's society, this third point isn't usually a problem because we usually end up having samples that are in the hundreds, tens of thousands, or like a million. Your sample size is size 1,000,000, in which case the skewness problem usually isn't going to be too much of a problem. But nonetheless, I should mention it because you should know that this sort of greater than equal to 30 mention, have a sample size greater than or equal to 30 thing that I've told you, it's going to work most of the time, but if you have really strong skewness, it's not going to work. Okay? So these are our three conditions. And there are things to remember, and there are things to check if you ever want to apply the central limit theorem. So to wrap up this whole CLT section, I'm going to end it with an example. The meals at an Italian family reunion are epically large. If you knew the standard deviation of calories at all of these meals is 800, and the population average is 300,000, so many. What is the probability that a simple random sample of size 60 gives you a sample mean of 3,050 calories or more? I'm going to put a little caveat. Assume your sample is not skewed. So I'm asking, what am I asking here? I want to know if the sample mean, what is the probability that the sample mean, x bar, is greater than or equal to this number, 300,050, right? So if I want to calculate the probability of x bar being in a certain group, I need to know something about the distribution of x bar to be able to calculate that probability. And to do that, we need to use the central limit theorem. So by this, let's first see if we can use the central limit theorem. So what are our conditions? So we need our sample of size 60 to be less than or equal to 10% of the total population. I think this is a pretty safe bet that there are a lot more than 60 big Italian meals happening in the world. So I'm going to say condition 1 is pretty well met. Condition 1 further is met because we took a simple random sample. So these values, they are independent. We randomly sampled and it was the correct proportion of the total population. I do have a sample size of greater than or equal to 30. My sample size is 60. Condition 2 is met. And it would appear, based on this little caveat I threw in the end, I don't need to worry about skewness because it isn't skewed. So all three conditions are met. And by the central limit theorem, x bar is distributed normal with, well, I want to know where my normal distribution is centered, right? That's just going to be centered at the mean, which we know what it is by our formulae. It is the expected value of the entire population, which is 300,000 calories. I want to know the spread of x bar. It's a normal distribution. It has a center and spread. And this is just going to be the standard deviation of the full population, which in this case is 800 divided by square root of my sample size, which was 60. And I went ahead and calculated this. It was approximately 103.2795556 calories. Cool. So if we want to know this probability, that is specifically going to correspond, let's see how I can draw this. You know, so many years of schooling, they never taught me how to draw. You're like a B minus, I think. So this is, since we said that our x bar by the central limit theorem is distributed normally, it looks like the distribution of x bar is going to look like this. It's going to be centered, as we just discovered, on 300K. And that means the probability I'm looking for is the probability of observing 300,050 calories or more. So that's going to be this area right here, right? And this is certainly something that we have learned how to do. We have all of the parts, so let's just move ahead with the procedure. We start by calculating our z-score. Our standard deviation is the standard deviation of x bar, which is calculated right here. So 103.2795556. I went ahead and calculated this for us. It's this number. We proceed to excel and use our norm.s.dis function. Which is this probability. But recall that the norm.s.dis function actually gives us the lower probability, and we want the upper. So what we do is we take 1 minus, which gives us our answer. With 0.31419.325 probability, we will observe a sample mean at or greater 300,050 calories. Okay? And this is, recall, this is for sample size 60. All right. And that is how you apply the central limit theorem. Any questions on this before we move on to our exciting new topic? Good? So, oh, this is fun. I like confidence intervals. I think they're cool. The next topic is confidence intervals and point estimates. So recall that we used the sample mean as our point estimate for our population average. And the picture here is that we have some sort of huge population, and there is a true average of this population, but we can't really calculate that average. We would have to observe every single individual in that average, and that's kind of unfeasible. So we take a sample, it's like this, and from the sample we calculate x bar, and that x bar is our point estimate that we use to estimate mu. So this right here is the point estimate. Right? This is the sample. This is the population. Anyway, so that was the idea, and we've been using the example of x bar as a point estimate for the true population average. The point I want to make first is that we can actually do this for any metric. We could use the sample median to predict the population median. Or the sample IQR to predict the population IQR, right? And so on and so forth. These values, so, are our best guesses They will likely be close to the true value, but they will rarely be equal to it. And actually, we had a picture of this yesterday with our simulation. Remember, I think it looks something like this. I know it looks something like this. So what did we see here? We saw a ton of different guesses. Every single one of these was an X bar. Every single one of these was a point estimate, recall? And note, yeah, they're all around the truth. They are all around the true population average, which you see in the dotted orange line. But note, almost none of them are. And I think, I was looking at this recently, I think one of them. So out of 200 guesses that we had, we got it right once. So how is this really helpful? I mean, it's cool that they're around the right answer, but if somebody asked me, what is the population average octopus tentacle length? And I gave you a number and I said, well, here's my best guess, but it's probably wrong. I mean, it's not informative, it's not exciting, it's not something that a researcher really wants to know. So let me see, I'll take a step back here, make this point explicit, that different samples, as we know, lead to different point estimates. And these samples, and these estimates, excuse me, will vary around the true value. We further know that by the central limit theorem, a very particular point estimator, the sample mean, bar, will, oh goodness, how do I get out of this? Oh my goodness, I'm so sorry. I don't actually know how to get rid of this. Go away. Go away. There we go. By the central limit theorem, the sample mean, a very particular point estimator, will follow a normal distribution around the population average in a very particular way. As expressed by its measure of spread. So yes, our guesses are around the right answer, and we actually know just about how much they vary around the right answer. So this next idea that I'm going to show you is called a confidence interval. And basically the idea is, here, I'll scroll back down. I'm sorry, don't worry. Basically the idea is, since my guesses, my point estimates, are never really going to be on the truth, what if instead of giving you point estimates, I gave you ranges of possible values that are centered at my point estimates, like so. When I do this, you'll note that the truth is contained in a bunch of these intervals. And in fact, these intervals are going to contain my truth a lot more than my points are going to capture it. And let me, if you didn't get that sentence, that's fine. I'm gonna present it in a number of different ways, and I hope one of these ways will click. So let's start with the definition of a confidence interval. A confidence interval is a plausible range of values or range of guesses for the population in this case, the population mean. So note that if we report just the point estimate, we will likely not hit the population parameter. Oh, and note, population parameter in this case is the mean, but whenever you say population parameter, that might mean as well like the population median, the population IQR, the population mu. It's just sort of like a general term for the different metrics of the whole population. So we'll likely not hit the population parameter. And this thought, the analogy here is think of fishing in a murky lake with a spear. So we report a range. And here you should think of fishing with a net instead. So putting down a point estimator, throwing the spear into the water doesn't always work very often. They're good guesses, but they're not going to be accurate. Whereas if we reported a range and said, well, the population parameter is likely going to be somewhere in this range, that's going to be a lot more likely to be true. It's going to, and it's the thought, excuse me, the analogy is like throwing a net down. Like, okay, so the spear's not going to work with some net and give you sort of like, it's going to be somewhere in here kind of situation. So without further ado, without further ado, let me give you the general formula for a confidence interval. So it's going to be the point estimate plus or minus C, which we call the critical value, times the standard error. And I'm going to give you general definitions of each of these, but don't worry, we're going to talk about how to calculate it specifically for problems that we'll run into. So this is the point estimate. So the idea is that the confidence interval is centered at our best guess, right? This is an interval, so we take our best guess and we subtract this value and add this value. So we're going to get a range of possible values that are centered at our point estimate. This is called the critical value. I'm going to talk more in a bit about how we calculate this, but for now I'm going to say this will change depending on the distribution of the point estimate and our level of confidence. And again, confidence is, I'm going to define it in a bit. This last thing is called the standard error. And this is often just the standard deviation of the point estimate. Okay, so these are all of the parts. To give you an idea of how they all fit together, I'm actually just going to dive into an example. So we want to do a 95% confidence interval of the mean. So let's do it. Suppose the length it takes to do a particular dental procedure is distributed normally with unknown population average and a standard deviation of 10 minutes. So note the really big difference here. Most of the other examples I've given you up until now, we knew what the population average is. This, we're finally taking that away. We're finally being more realistic to what you would come across if you were doing this in the real world. We don't know what the population average is, and we're going to see what we can say about it. Inference. So we do, however, know the population standard deviation in this example. And what I'm going to say is that you want to know the population average, so you take a sample. Of 30 procedures. And observe that the sample mean is 95.2 minutes. And again, I'm going to say assume sample isn't skewed. Okay. So this is our situation. Let us build a confidence interval to determine, or I guess say what we can say about the population average. So first step is you need to define this thing called alpha. So you want to let alpha equals to be equal to 1 minus your confidence level, your confidence. So in this case, I want a 95% confidence interval, is what I said. So this is just going to be equal to 0.95, okay, or 0.05. I'm going to talk a little bit more about alpha in a bit. For now, it is just a variable that we need to plug in a second. And I'm going to talk more about confidence in a bit. But I think in my experience, it's best to sort of see it, and then I'm going to build more intuition about why we did each of these steps. So first thing, calculate alpha. Determine what alpha is, determine your confidence. Step 2 is to calculate all the different parts. So what did we need? We needed a point estimate, a C, and a standard error, right? So we'll start by saying what our point estimate is. And that was just what our X bar was. So we took a sample of size 30 and we got 95.2, so our point estimate is 95.2 minutes. Okay. Next thing we need is our standard error, which, as I said, was just going to be the standard deviation of our point estimate, which is x bar. So we need to know standard deviation of our point estimate, which is just the population standard deviation divided by root n, which here is going to be 10 over root 30, right? I think I said it was 10 minutes. Yeah, population standard deviation is 10 minutes. We took a sample of size 30, that checks out. And this is going to be approximately 1.826 minutes. Okay? And the next thing we're going to calculate is this critical value C. And C has to do with the distribution of x bar. And because of that, you need to calculate C, you need x bar to be normally distributed. So this whole process only works if we can argue that x bar is a normal distribution. And there are two ways that we can do this. We can say if the underlying distribution were normal, we would be good, which does actually happen in this case. The underlying distribution was normal, so we didn't need to apply the central limit theorem. We just get it automatically. But note, if we didn't have this, we could still calculate C. We would just have to check our conditions for the central limit theorem. So our estimate is normally distributed. So the way that we calculate C is it's going to be this right here. And this is the alpha over 2th percentile of the standard normal distribution. Or to give it in a picture, it's going to be the z-score such that the area beneath it is equal to alpha over 2, right? That's what that is. This is just this like z sub alpha over 2. It's shorthand for specifically what this is, the alpha over 2th percentile. Okay? So, I mean, it's easy for me to say it as a variable. Let's actually plug in what it is going to be in this case. This is going to be z of, what was our alpha? 0.05, so 0.05 divided by 2, which we actually had a Excel function to do this for us. So this is norm.s.inverse of 0.05 divided by 2, which I think is 0.025, right? Which is going to be equal to the absolute value of negative 1.95996, or just 1.95996. Okay, so that's C. So we found C, it's right here. We have found the standard error, it's right here. And we have found our x bar, it's right here. So what we need to do is put them all together. So the 95% confidence interval for x bar is whatever x bar was, so 95.2. Our point estimate plus or minus C, which is 1.95996, times whatever our standard error was, which is 1.826. And this is going to give me a range of plausible values. So it is, I think I went in and calculated this, so 95.2 minus everything over here is 91.62113, and 95.2 plus everything over here is going to be 98.77889. So if instead of just giving somebody our point estimate, 95.2, we could give them this range of values and we could say we are 95% confident that our true population average, that this, we are 95% confident that this interval contains our true population average. So maybe I'll write that down. The true population average, which I think is a lot more informative. But the next question you should be asking, which is a very good question. So what does confidence mean? Notice I didn't say with 95% probability, which is an idea we do have. I've introduced this new term, confidence, and then I kind of glossed over what it meant. So let's go back. Let me tell you what this actually means. So our goal with a confidence interval is to capture the true population parameter mu. And notice that if we draw a different sample that we'll get a different interval. So just like with our x bar, if we drew a different sample, we would get a different x bar. Well, if we drew a different sample, we would also get a different confidence interval. So what does confidence actually mean? And I have a picture for this. Crap. So this is our true population down here. The true population mu, which we don't know. Or at least we say we didn't know when we made the intervals. I'm doing an example, so I'm just telling you the truth is right here. And each of these are confidence intervals that are centered around the sample mean. So this is like x bar star, I took sample and got the first sample mean. This would be like x bar, what else did I use? Like crescent moon. This one's like x bar, smiley face, and so on and so forth. Every single time I take a sample, I get a different x bar. And as a consequence, I get a different confidence interval each time I do it. And with 95, so this is, let's say, these are all for sample size 30. So what is happening here is I'm building a lot of confidence intervals, and I'm building them all the same way, and I'm getting a bunch of different ones. And what 95% confidence actually means is that if we made a lot of these intervals repeatedly, a ton of times, 95% of them, approximately 95% of them, would contain the true population average mu, which is actually what we see here. Look, a bunch of these intervals are doing pretty well. When I make them, they do indeed, in fact, every single one in the blue does indeed contain the true population average, mu. But there's one that doesn't. This time I took a sample in the red here, and I didn't. I made a confidence interval that didn't actually contain the true population parameter mu. But the point is that that doesn't happen very often. And in fact, if I were to do it many, many times, 95% of the time, my confidence interval will contain. And that's kind of what you're seeing here. I did it a bunch of times, and most of the time it worked out. One or a couple of times over the long term, it's not going to work out, right? So when you present one of these intervals to people, you can say, this is an interval I am 95% confident contains the true population average mu. And what you're saying is, well, if I were to do this a ton of times, 95% of the ones that I did would be true confidence intervals. They work. They did exactly what I say they do. And about 5% of the time, they're going to be wrong. And that's what confidence means. So let's see. Let me try to write this in a more succinct way. A 95% confidence interval is an interval. Interval that if we made it repeatedly, we would expect approximately 95% of them to contain mu. All right, so we have our confidences. It's not probability. It's saying that 95% of the intervals made in this way will do what I say they do. So there's a small nuance here. And that is, why didn't I say probability? Why didn't I say with 95% probability my interval will contain mu? And that is because mu is not a random variable. So this is a slight nuance. If you don't fully understand this, it's okay. I'm going to dive into it for a hot sec. But the overarching picture here is that don't say that sentence that I just said. Don't say that not with 95% probability my interval will contain mu, because it's not actually correct. And if you say that to somebody who knows what they're talking about, they're going to think that you don't know what you're talking about. So a sentence to be avoided, use the word confidence. And the reason we use the word confidence is, so let me, okay, one second. So this is not the same as saying will contain mu with 95% probability. And this is because mu, the population average, is a fixed number. Not a random variable. Right? If I were to collect every single octopus tentacle in the whole world and calculate the average, that would be a single number. It wouldn't change. It does exist. I just can't really calculate it, so I'm making guesses at it. But I'm making a guess at a number that does exist out there, just we as humans can't really precisely figure it out. And because it's a number and not a random variable, each of these intervals will either contain mu or not contain mu. Since mu is a number, the probability of my interval containing mu is either 0 or 1, which is, it's nuanced, and I hope you get somewhat of an idea of it. And the whole point of this is to use the word confidence. So this is why we've introduced the language of confidence, specifically because we're trying to sidestep this issue. We can't say probability, so we set a new word that we can say. Okay, so I'm going to do one more example with these confidence intervals, and then that is going to be it. I go in it for this lecture. I go into it a little bit in more detail in the lecture video. So let's do this example, and then I'll stick around for any questions. Or are there any questions now? Okay. You're all pros at confidence intervals. The feather lengths of peacocks are known to be distributed normally. You take a sample of peacocks and find your sample mean to be 18.3 inches. I'm going to say with a standard error of 4 inches. Find a 99% confidence interval for the population average mu. So we don't know the population average, but we can make a confidence interval to say something about the population average. So the first step is to calculate that weird alpha number. And I'm going to give you another point about alpha. It's called the confidence level. Just for future reference, that's what this alpha number is. I'm actually going to talk a little bit about it in like 2 lectures, but for now, just know it's 1 minus whatever your confidence level is. So 1 minus 0.99, 99%. So my alpha in this case is going to be 0.01. So that's step 1. Step 2, let us calculate all of our different parts. So our point estimate is just going to be x bar, which I think we get in the problem, right? 18.3. Cool. Our standard error is actually just given to us. We don't need to do anything fancy. It told us that the standard error is 4 for this problem. So we got a little bit of a freebie in that regard. And then our C value, we first check to see for normality. So let's see. Oh, it looks like feather lengths here are distributed normally. So we have automatically that x bar is normally distributed. But note, if I hadn't said that they are distributed normally, you would have to check your conditions for the central limit theorem to be able to use this. So we check for our normality, and because of that, we use that C is equal to the absolute value of the alpha minus 2th quantile of the standard normal distribution, which is equal to, we can use Excel to calculate, it is norm dot s dot inverse what is it, 0.01. 0.01 over 2, right? And that is just going to be equal to the absolute value of negative 2.57583, or 2.57583. Okay? So we have our C, we have our standard error, we have our point estimate. These are all of the things that we need to calculate our confidence interval. So it's x bar plus or minus C times the standard error. This is 18.3 plus or minus negative 2.57583 times our standard error. So this is C, and this is our standard error 4, and this is our x bar. And if you calculate this all out, you get 7.99668, and then 28.60332. So I would present this confidence interval, and I would say we are 99% confident that our true population average falls in this range. Okay? So that was my final example. We're going to be going over some other details and some other interesting things about confidence intervals in the next lecture video. And I don't know, be excited. This is our first instance of true inference in this class. So we have this unknown quantity, this mu, and this is something we can say about it. We can say an interval. Okay, any questions?
I have
one. Of course.
So like when you have it in the absolute value, it's like negative 2.5783, and then it becomes positive, right? Why does the negative stay when you plug it into the formula for the?
Oh, it shouldn't. I'm so sorry. That shouldn't be there. To answer your question, because I wrote the wrong thing. Nice catch. Thank you. Any other questions?
Oh, go ahead.
Sorry. Is there any reason to like not make your confidence interval like as high of a percentage as possible?
Oh, as high of confidence.
Yeah.
Yes, in fact there is, and that is one of the major topics in the lecture video. So great thinking ahead, Leo. And Con?
What do you mean? I guess like if it doesn't say it's normally distributed, what are we checking for normality to solve for what, I guess?
Yes, so we used a standard normal distribution here, right? And we can actually only use that thing as our critical value if we have that x bar is normally distributed. And that actually gets to something a little bit more complicated. I might go into it more later, or if you like to talk about it during office hours, I would love to give you a rundown. But it's an important point, but you don't necessarily need to fully understand it to be able to use a confidence interval.
Okay.
Yeah.
Okay.
Any other questions? All right, well, thank you so much, everyone. I'll stick around if anyone wants to talk after class, and that is it for today. Your homework should be posted at 4:30.